It's an honor to be the speaker at the 526th Convocation of the University of Chicago. Welcome students, friends, family, welcome. I first want to start, of course, with congratulations to the graduates. You will soon receive your well-earned degree from the University of Chicago. Several years ago, you seized an extraordinary opportunity, and through your hard work, perseverance, find yourself here today. Not many have the opportunity or the ability to do what you have done, and you know it wasn't easy. Many have invested in you, none more than you have yourself, and I thank you. We all thank you for that. What have you learned? Well, you've learned a lot beyond the facts that you probably will forget soon. You have learned how to learn. You learned the value of learning. You have learned how to think. This is hopefully giving you a deeper appreciation of life and giving you more opportunities to be inspired. You are ready to explore and to contribute. You're ready to seek your path wherever it may lead you. Frankly, this took me a long time. In fact, I'm still kind of working on that. But then again, I didn't have the benefit of a University of Chicago education. Today, I want to tell you a few stories. I'm going to start with a vague memory, just to remind myself even. I had a vague memory of my father coming home from work once and saying he heard a news story where on the news that they said that scientists had heard the universe being created. I don't remember too much of that, but somehow I buried that deep inside. I also remember my mother, who was taking night courses to get her degree at the time, coming home and telling us about what she learned in classes. I especially remember her telling us about the stars, about galaxies, about space, and Einstein's outrageous, it seemed to us, theories. It was a lot of fun to try to get our heads around this. Space and time weren't fixed. They could be curved, they were immutable, they were relative. There were black holes. It was a lot of fun, but it was very inspiring. All right. These are strange ideas to us, of course. They're far from our everyday experience. But Einstein was a clear thinker. Einstein was able to distinguish and separate what was known to be fact by observation and what was just assumed to be real. Right? Taking that and taking what was the result of experiments at the time, observations of the universe, led him to these really incredible and unimaginable or outrageous, people would think, insights in how the universe worked. And we now know those insights and his results were true. Our Chandrasekhar here at the University of Chicago was also a masterful thinker. He showed how the death of massive stars would turn into black holes at a time when most people didn't believe there were such things. I am lucky, indeed privileged, all these many years later to be studying the universe. That news story my father heard must have been about the discovery of what's called the cosmic microwave background. This is a discovery made by two Bell Lab scientists. They had found that there was a glow of light. The universe was glowing with light in all directions. It was light that was at very long wavelengths, what we call radio waves, in which you can't see with your eyes. And as a result, I suspect that's why it got confused in the story to be hearing the universe rather than seeing the universe. They had discovered the very first light in the universe, the fossil light from the hot Big Bang that has been traveling to us for nearly 14 billion years. This cosmic microwave background, or background radiation, is an amazing thing. It provides us with a glimpse and actually the ability to view and see the early universe 14 billion years ago, to a time before stars had even formed. It gave us, the discovery expanded our view of the universe and gave us a tool to discover it. That's the tool I use this day. Some of you, the undergraduates, maybe remember in phi-sci classes measuring the cosmic microwave background, using instrumentation very similar to what Penzias and Wilson used. Bob Wilson actually called me once and said, "How do you do that? How is it that you have undergraduates at the University of Chicago measure the cosmic microwave background? We want to do that at Harvard." That call made my day, I can tell you. It has taken decades, however, using ever more sensitive telescopes and sensors to go beyond the detection of the cosmic microwave background to actually develop baby pictures of our universe with enough sensitivity that we can see these very faint features in the early universe. All right. And we have done that. The most detailed images come from the University of Chicago-led South Pole Telescope. It's located on the driest desert on Earth, the high and cold Antarctic plateau. It's there to take advantage of the exceptionally clear skies. Working at the South Pole is really fascinating. You know, it's cold. Probably you knew that. It's actually colder than Chicago. Maybe you didn't know that, except for 1 or 2 days a year when we find that actually it's reversed. But usually it's quite cold. The most inspiring thing, I should also point out the views are just amazing. It's like something you've never seen, just ice, snow, beautiful. But the most inspiring thing is not the views, it's the people. There's about 200 people at the research station during the austral summer, about 3 months. And then only a handful, 50 at most, decide to spend the night, the long winter night there. And they keep it going. They keep it going, and for 9 months they cannot leave the station or come in. It's closed off. Right? There's no physical access whatsoever. They all work together, they have a common purpose, and they all have a part to play. They share in the discoveries, which would not be possible without them. They are inspired, and they're inspiring. So what have we learned? Well, a great deal. We have figured out what stuff makes up the universe, and amazingly, the stuff we know about, the stuff you can find in your textbooks, is a whopping few percent, 4%. We know the other stuff is there. We even give it names. We give it names that inform, are informative of our knowledge of it. We call it dark energy and dark matter. Clearly, there's a lot more to discover and to learn. So we make these baby pictures, but what do they look like? And the truth is, they look like noise. But if you're educated and you can appreciate this noise, the noise is exactly that would be predicted. It's beautiful. It's exactly that would be predicted by quantum mechanics. In fact, what they are a picture of is quantum fuzz. This quantum fuzz, which rules physics on the scales that are unimaginably small, has somehow been expanded to the astronomical scales and to give the seeds of all the structure in the universe, including, ultimately, us. Right? Our alumni, Carl Sagan, famously said, "We are star stuff," referring to the fact that most of the elements that we are made out of were first made in stars. We can now say we are quantum fluctuations. I agree, it's not quite it might not sell as well, but it's an amazing fact, or appears to be a fact, that we are the result of quantum fluctuations all that long time ago. Let me tell you another story. Roughly 1 billion years ago, in a galaxy far, far away, 2 black holes, like the type predicted by Chandrasekhar, began a death spiral, orbiting each other closer and closer. The extreme gravity of each hole warped and distorted the space-time around it and dragged it with it. And as they circled each other, the fabric of space itself emitted waves, what we call gravitational waves. Those gravitational waves spread out, propagated through the universe, moving at the speed of light, and carried away energy. The black holes then collided, losing energy, spiraled in even closer till their ultimate, inevitable, catastrophic collision. In a fraction of a second before they collided, moving at a relative velocity close to the speed of light, they emitted a final burst of gravitational waves that Einstein predicted. Those waves carried off more power during that brief time than all the light emitted by all the stars in the universe. They then merged into a single black hole with a mass about 60 times the mass of the sun. Now that was one hell of an event. 40 years ago, scientists began to develop a method to try to detect gravitational waves with a bold, some might say even outrageous, goal of using them as a way to observe the universe. They needed to figure out how to measure the ridiculously small and fleeting changes in space and geometries introduced by the passing of a gravitational wave. So what is ridiculously small? Well, it's a part in 10 to the 21, one with 21 zeros followed it. So that's as if your gravity wave went through, it's as if your toes got closer to your head by a dimension of 1/trillionth the size of an atom, and then vibrated back and forth at maybe 100 hertz, a frequency which you could hear, if it was loud enough, for a fraction of a second. So another way of looking at that is if you take the distance to nearest star, not our sun, but let's say Alpha Centauri at 4.4 light years, it's the change in distance over that great distance of the width of a human hair. An incredibly hard and difficult thing to do, and many thought impossible. To attempt these measurements, over 1,000 scientists from 15 countries carefully and meticulously refined what's known as interferometry. It's a technique pioneered a century earlier by Michelson, a great Chicago physicist. They used what's called a Michelson interferometer to measure precise distances by bouncing laser light off 4-kilometer distant, heavily stabilized mirrors. After solving problem after problem, challenge after challenge, last fall they reached the stage where they had sufficient sensitivity to hope to make a detection. And it was just in time. They turned their machines on. 4 days later, those gravitational waves from that merging black hole 1 billion years ago reached Earth, passed through Earth, and set off their detectors. We all heard about this on February 11th. The whole world learned at it on February 11th. We heard this story directly from our colleagues who were part of the discovery team, Professor Dan Holtz and his students. That is the same Dan Holtz that the undergraduates nominated last year for Quantrell Excellence in Undergraduate Teaching Award, and of course he received it. Once again, our view of the universe has expanded with a new tool to explore it. In many ways, we are now actually hearing the universe. When I got home that day, I told my children all about it. Astronomers will now begin to investigate the properties of black holes directly and their role in the evolution of the universe. Maybe decades from now, your children will be measuring gravitational waves in a phi-sci lab at the University of Chicago. There is one more incredibly energetic event, the most energetic event in the history of our universe, which is the birth of our universe. Our model of the universe, which fits all the existing data so well, predicts that in the first fraction of a second after the Big Bang, and by that I mean 10 to the minus 35 seconds, is what my colleague Michael Turner refers to as a jiffy. So in one jiffy, gravitational waves, a whole background of distorted space-time should have been produced and left as a background. We believe we know how to see that background now by making incredibly sensitive, some say outrageously so, measurements of the cosmic background. And if we find them, we can then use them to explore our origins. We're starting the experiment. We already have hundreds of scientists from across the globe coming together, and hopefully you will not have to wait too long to hear about the results. But when you do, please tell your children. So what is the message behind these stories? Well, you can use your exceptional education, dare I say privileged education, to make a difference in whatever you choose to do. Please be bold. Know that people working together can achieve great, even seemingly impossible things. Go and make a difference. We're counting on you to do that. In closing, let me again congratulate you and thank you for all your hard work. Many thanks to your families and supporters. Keep learning and teaching. Be inspired and inspire. Whatever you choose to do, do it well. Share your story, and please come back and tell us about it. Thank you.